Good evening, everyone. Welcome to Skillings webinar series. We'll wait for another 10 minutes for the participants to join.
Listening zone.
तुम्ही ऑडिओ पूर्ण बघा. Okay, right.
Good evening, everyone. Welcome to Skillings webinar series. We'll wait for another 5 minutes for the participants to join. Good evening, everyone. Welcome to Skillings webinar series. For suggestions or interesting topics, please write to Satish Jesu at skilling.com. He is the head of the product. For certificate-related queries, please write to Diana at skilling.com. She is a project engineer. For course-related queries, please contact to sales@skilling.com. You can also connect with us at www.skilling.com, LinkedIn, Facebook, and Instagram as well. Important points to be noted. All the participants will be here for the session. If you have any questions in the course of the presentation, you can feel free to drop them in the chat box. We shall bring them up during the question and answer session. We request all the participants to stay till the end to get your certificates. A certificate link will be shared in the chat box at the end of the webinar. To be issued with a valid certificate, please make sure to give us your right credentials. Jagat.
Uh, Good evening to all. Thanks for the introduction, Mirunali. Can I share my screen now? So I think you have to
Yes,
give
yes,
access to my
yes,
screen share.
yes, Dr. Jagat.
Yeah. So my audio and this PPT is visible to everyone.
Yes, it's visible.
Okay, thank you. Hi, I'm Dr. Jagat. So today webinar I'm going to present on the topic of introduction to the thermal fluid sciences. So so first we'll see the background of thermal fluid sciences and some of the categories in terms of applications of thermal fluid sciences. Thermodynamics, what are the basic definitions and what are the things like laws of thermodynamics and problem solving techniques in different ways and basic terminology and what are the requirements to go through in particular fields called thermodynamics, fluid sciences, and heat transfer. So we'll go through one by one. So what is it actually? What is the background of it? And we'll end up with the introduction to the fluid mechanics. Uh, at the end, I'll focus more on the research areas and more the trending or the emerging technologies where the thermal fluid sciences can be applied. So I collected some of the information which are having a major and the universities which are performing. So these kind of simulations or experimental analysis or whatever the content they are going to do in a particular field of thermal fluid sciences. So I'll just present in that particular fashion. So okay, let us jump into the actual webinar. Uh, well, I'll start with a brief introduction to the background of thermal fluid sciences. So, when we talk about the thermal fluid sciences, so we are talking about actual energy. So, physical science that deal with the energy and transport or conversion of the energy are usually referred as the thermal fluid sciences. So, if you look at the foundation of thermal fluid sciences, which is basically studied under the subcategories of thermodynamics, heat transfer, and fluid mechanics. So, if you look at the broader aspect of introduction to the fluids, thermal science or thermal fluid sciences, so it actually presents the basic principles of all these three. So, if you are well good in the basic principles of all these heat transfer, thermodynamics, and fluid mechanics sciences. And this particular science, thermofluid sciences, will teach us how to apply them, how to apply the basic principles of so these all streams to the situations that engineers are likely to encounter. So in their actual practice or maybe in the industrial problems. So if you look at the design and analysis of most thermal systems, such as power plants, automotive engines, and refrigerators, etc., involve all categories of these thermal fluid sciences, and also as well as other sciences which maybe involves such as material science or maybe a strength of materials, or etc. So this is kind of a mixed intervention of all these streams together to solve any kind of a physical problem. So, so the reason to study these kind of a particular streams or the sciences separately is just simply to facilitate the learning, being overwhelmed. So that kind of enthusiasm, or maybe if you study all an individual manner and club together to get knowledge. So these are under one umbrella you can just think of. So once the basic principles are mastered by any person or any student or any industrial expertise, so they can then they can do the synthesis of all these streams and then able to solve comprehensive real world practical problems. So that is the motive of understanding of this particular thermal fluid sciences. So this is a kind of advantage we get if you learn such kind of subjects, or maybe the streams, whatever the way you just call it. So, so moving further, so this thermal fluid science is actually built up. So this slide shows the thermal fluid sciences built with these substreams, which we call fluid mechanics, thermodynamics, and heat transfers. So, without taking much time, so let me split and introduce one by one. Thermodynamics, so when we study the science of energy, and it converts to work to heat or heat to work, vice versa. So things like you just imagine ice engines, phase changes of fluids, and so these are not limited, it's a lot more. And coming to the transfer, so where we study the transfer of energy, not the conversion of the energy. So in both materials and fluids. So think about the process like convection, conduction, and the practical example you can just think of heat transfer from a flame into some water in a pot in order to boil it. So this is a kind of example we can provide for us, just a simple understanding of how this the energy is transferred, not the conversion of the energy. And we'll talk about much detail in the slides. And when it comes to the fluid mechanics, so where we study the mechanics of the fluids, both in motion and rest. So if the fluid is in motion, we call them as dynamics of the fluid, and it is at rest, statics of the fluid. So whatever the category, subcategory it is, so we study how this actually functions, and in detail, if you go through it, linear, non-linear, and all these comes into the fluid behavior to understand the fluid behavior. So, as an example, things like buoyant forces on an object in water, such as iceberg,
Dear participants, sorry for the inconvenience. Kindly hold on.
So I'm sorry for the interruption.
Yes, you can continue, Dr. Jijan.
Okay. So can you just tell me where it got stopped? Which slide? Sixth slide, I think.
Yes, yes.
So this slide is visible, right? I think.
Yes, it's visible.
Yeah. Okay. Fine. I'll just revise the slides and I'll quickly go to the next slide. Uh, so in a broader aspect, we can split so all these three subcategories, and we have given some kind of examples. So thermodynamics, where we study the science of energy conversion from work to heat, vice versa. So some of the examples, IC engines, phase changes of the fluids we have given. And in heat transfer, we study the transfer of energy, not in the conversion of energy. So that maybe happen both in materials and fluids. So just think about the convection process. And when it comes to the fluid mechanics, so where we study the mechanics of the fluid, both in motion and rest. So fluid statics of the fluids and dynamics of the fluids. So best example we can provide is the buoyant forces on an object. So in a water such as iceberg. So this is the best example we can provide as a basic example. So this not might be in an engineering oriented example, but in a general sense we can provide this particular example. Or maybe flow or aerofoil. This is an industrial oriented example for providing a lift for an aeroplane. So all these aspects, if you combine together, uh, one thing is common in each of these topics, which is energy systems. All these are converged sort of border area. So where we just synthesize all these three streams to the knowledge of all these individual core courses to understand how this design or engineer the devices for efficient. Ultimately, we have to get the efficient energy conversion systems. So that is the motto of all substreams where we can go to understand the individual aspects of these particular streams. So, moving on. So, am I audible? And the PPT is visible because somewhere I might get disconnected.
It's
It's okay?
visible. Yes, yes.
Yeah, fine. Thank you. Thank you. And when it comes to the application, so everybody is know this particular streams where we can apply these kind of examples. So it is a known fact that all activities in nature, which somehow it involves some interaction between energy and matter. So it is hard to imagine where you cannot have that particular area which doesn't relate to this particular thermal fluid science in any matter, in any sense. So that is the excitement it provides to understand what are the principles uh, involved in it to understand this particular thermal fluid sciences, where developing a good understanding of these basic principles of thermal fluid sciences has that is also very important and has long been essential part of engineering education as well. So coming to the each and some of the applications. So here some of the applications have presented. One such example is a solar water heater. So here in this example, solar energy being converted to heat and heat collected by the water, which is flowing through the solar collector. So just imagine heat is collected by the water and which is flowing through the solar collector. So the water then collected in the hot water tank. So this can be used for shower or any other purposes. So here we see this thermodynamics, change in temperature of the water, then energy transfer. If you look at the heat transfer where it is appearing, so the rate at which the heat of the water is increasing, then the rate at which the energy is being transferred to the system. So there you can just imagine the concepts of the heat transfer and why this fluid mechanics also plays into major roles. The flow through the pipe in uh, any kind of a material. So that is also a good example of this particular fluid mechanics. So the study of all together under one umbrella, so which provides to develop efficient solar water heating system. So this is the general example. And if you look at the other application, so this is also interesting applications. If you um look at the uh, bio-related applications. So let us think of a human heart. Heart is constantly pumping blood to all parts of the human body. Various energy conversions occur in trillions of blood cells. So everybody know it, and the body heat generated is constantly rejected to the environment. So that is also a well-known fact, and we might not see how much quantity is ejected, how much energy you are taking in. And all these aspects are very interesting to study. So the human comfort is closely tied to the rate of this metabolic heat reduction system. So we try to control this heat transfer rate by adjusting our, some of the wearing clothes system, or maybe putting the environmental situations like that. So we can adjust this heat transfer rate. So apart from that, any defects in the heart or a circulatory system provides information for the future problems. So that is also one of the advantages, and it gives. So if you understand these kind of principles and know the problems where you can study and get the solutions, or maybe the precautions need to be taken to avoid these kind of situations, or maybe to avoid these kind of problems. So this is where we study the fluid flow or the dynamic nature of the flow, and the effects of the viscosity also. We may get a chance to learn in the pumping system. So this is a kind of application we can think of. Moving on, other applications. So another good example, designing the radiator of the car, which involves the determination of the amount of energy from knowledge of all the properties of the coolant using thermodynamics. So that determination of the size and shape of inner tubes, where we talk about when we talk about the radiator, the flow of the uh, fluid system, and outer fins also. So which is basically depending on the heat transfer. So size and shape of the inner tubes and outer fins will be uh, designed based on the heat transfer concepts. And the determination of size and type of water pump, which is to be used, which will decide by the basic principles or basic knowledge of the fluid mechanics, or maybe the concepts which used or applied to find out the size and type of what kind of water pump need to be incorporated in this particular application. So of course, Yeah. So, so if you look at the radiator or refrigerator or air conditioning system, so all together, so these are all the type of applications you can just think of which uses a lot of principles from the thermodynamics as well as fluid mechanics. Um, Another application, such kind of application, once management of electronics. Maybe we'll talk about this because this is an emerging area where we can use the thermal fluid sciences in rapidly all together in a batteries, laptops or old versions. Maybe we'll talk about that also in in the research areas where the people or the researchers or the scientists were so they are trying to invent new kind of principles or maybe approach how to utilize this particular thermal fluid sciences in a particular fields. And another application, such kind of applications, you can just exploring the science beyond the Earth atmosphere. So where you study, you can just think of the study of fire and combustion in, let's say, gravity-free environment eliminates the compounding factors of the buoyancy, the flows, allowing us to better understanding and the underlying physics of fire dynamics. Such kind of systems where you can just think of this particular thermal fluid sciences, and in addition, you can see to how to analyze the material flammability or fire safety on the earth. All these things will also be a very good area of research. So the research in other areas of the fire science, such as conduction and explosion of fires in both larger areas or confined areas. So opportunities such as a development of this particular state art is combustion models or mesh free technique simulation. So these are some of the numerical techniques which can be used to solve any kind of real time problems, um, where you can just think of applying these principles to get energy efficient systems or the buildings. So this is the motto of understanding of so these particular thermal fluid sciences. So in a overall sense, we can just give a brief introduction of comparing with these kind of applications. So many ordinary applications are designed in a whole or a part by using these principles of TFS. Some examples you can just think of some of the other examples: electric or a gas range or heating or air conditioning. I think we mentioned already air conditioning system, the refrigerator, humidifier, pressure cooker, etc. All these things will also be matter, and even in our day-to-day life, computer, TV, DVD, all these are one way or other. It is interlinked to these principles of thermal fluid sciences, and it plays a major part in the design and analysis of automotive engines, rockets. These are all in a larger scale engines, rockets, jet engines, and nuclear power plants. So that is also need to be mentioned. Solar collectors, uh, maybe other systems, and particularly if you just think of a water distribution system in one of the example in the cities. So this is also one of the important aspects of the fluid flow, and also design of vehicles in ordinary cars or aeroplanes. So just change of the design is also needs to be taken care of all these aspects. So once you just think of a design is changed, and do you apply the same principles? Yes, of course we'll apply the same principles, but the effect of the analysis for the different design or a modified design will be different, and that kind of a results also we need to be taken care in the solution provision, or where you can give the efficient systems. So that is also be a kind of a mm, considerable point to be understood. So the energy efficient systems where uh, the size and location also matter for a particular design system. So I think the PPT is visible to you, right?
Yes, yes, it's visible.
Can you hear me? Just say okay.
Yes, yes, you're on.
Hello.
Yes, you're audible.
So, if you just think of thermal fluid sciences, which involves application of experimental techniques or mathematical methods, so based on various principles, physics, fluid and gas dynamics, and heat transfer, to develop and operate energy conversion systems such as solar panels or maybe wind turbines or internal combustion engines, all these categories. So, in a general sense. Uh, Engineers frequently use an advanced thermal fluid technologies to design safe and more efficient systems. So, if you talk about in detail, that thermal science first examine which is physics that examines the interaction of temperature, pressure, and volume. So these three are the basic
Dr. Jagat,
parameters or the properties within
keep it in
system
full screen?
which converts
Dr.
the
Jagat?
heat to work or vice versa. So it is governed by some of the universal principles or maybe
Dr. Jagat, can you keep it in full
universal
screen?
laws. So these implications of reach beyond the engineering and even as for philosophy is also concerned. So first rules state the energy or matter cannot be created or be destroyed. So this is kind of a thermodynamic basic rule. Uh, it can only be converted from one form to the other. Everybody know it. So this is not a new thing, or maybe in the graduate level, or maybe in the basic science level. So you might have heard this rule: energy cannot be created nor be destroyed. It can be converted one form to the other form. So this is a kind of a first law of thermodynamics you can just think of, and the second law which says all machines will lose some kind of energy from input to output. Obviously, you cannot expect the 100% efficiency of any kind of a system, not only a human body, or maybe in terms of machineries, or maybe other things which will not be able to produce 100% efficiency. So there will be some losses. So in a process, we call this as an entropy, that the rate of change of the system. Uh, with respect to the temperature or the time. So the second important aspect is the heat transfer, right? So which is actually concerned with the exchange of heat between physical system. It actually involves the mechanisms. We already talked about conduction, convection, radiation, not in detail, but as a terms. And the transfer of energy by phase changes. So they always occur in a region from high temperature to the low temperature because heat transfer in a similar fashion. So heat, conduction or diffusion or any other direct microscopic exchange. Uh, One second. Yeah. So in this particular heat transfer aspect, so we talk about all these different subcategories. So just imagine heat convection occurs when the bulk flow of fluid carries heat along with the fluid flow, and the fluid flow of the fluid may be forced or external, so that kind of systems we may go through some kind of uh, relevant principles. Based on the principle, just go through the solution, building some kind of methods which involves to solve this kind of a problem. And when we talk about the fluid mechanics, so the solids or gases or plasmas, we just talk about all these subcategories. Uh, well, to the planetary level, fluid mechanics can be, just think of various fields from fluid statics to the study of fluids at rest, and fluid kinematics, the study of fluids and dynamics, which are the study of effective forces on the fluid motion. These three categories will be studied in fluid mechanics. So fluid dynamics can be, just think of mathematically complex and is an area of research where many unsolved problems can be solved, and applying these principles of combination of all these three subcategories. Advances in computational science also evolved rapidly and have facilitated effective implementation of numerical methods in this particular field. Modern disciplines such as CFD, computational fluid dynamics. So these are the subcategories of thermal fluid sciences. Just move on. Why this is so different from the heat transfer and thermodynamics? So we'll take one definition, and we don't have much time. I think it's only because of so many distractions. It's okay. Anyways, so I'll just quickly go through some of the basic definitions which you might have already learned in the past. So I'll not take much time, but I'll trigger to activate some consciousness on these concepts. Let me start with the definition of heat. Well, it is a form of energy, so it can be transferred from one system to the other system to due to temperature differences. So this definition, everyone know it. It's not a new, but to understand is word, both thermodynamics and transfer. If you look at in depth, thermodynamics is how heat is transferred, how work is done, and what is the final state of the system. Whereas the heat transfer tells us how heat is transferred. It is not telling us how much heat transferred, but tells us how heat is transferred and what rate of heat is transferred. So at rate heat transferred. So the temperature distributions, maybe the inside system, so that are also it you can learn. So that is the differences you can just make out with the basic definitions. In engineering problems, we are often interested maybe the rate of heat transfer is topic of science of heat transfer. So that is a kind of a study you can think of. So this is the difference you can we already discussed. So then just basic definitions we'll just have look at. Energy, it is the ability to cause a change. Conversion of the energy can be transferred from one form to the other form, we already discussed. So however, the total energy remains constant. That is the condition or the rule. Energy can neither be created nor be destroyed. That is the basic idea of understanding. So there are different kind of thermodynamics. So these are basic definitions. Classical thermodynamics, where we see only macroscopic approach, and statistical thermodynamics, where we see microscopic approach. Maybe we'll uh, just see some of the laws where we understand what kind of thermodynamic systems we use in a general sense. So, so this zeroth law says two systems are in contact or in equilibrium with the third one, and two systems themselves are thermal equilibrium. So that is a kind of zeroth law. So we'll briefly we'll just see. And first law deals with principles of conversion of the energy. So we already discussed, right? First law, we may not expect these kind of a conversion. Complete conversions may not be possible, but you can deal these kind of principles. Internal energy of the system equal to the difference heat transferred into the system and the work done by the system. So let's assume one machine uh, is continuously evolving some kind of heat. Just take the human bodies. That is best example to illustrate the first law. How much, what is the difference between heat transferred into the system and what is the work done by the system? And that is the kind of a value or the quantity which says what is the internal energy of the system. And coming to the second law, this the change or the state of entropy of the entire universe will increase over the time. So that is, it will be never-ending process. And the third law says absolute zero temperature is unattainable because you may not able to maintain such kind of a systems, or maybe you may not be able to create that kind of a system to make that in an equilibrium position to maintain at a zero particular temperature. That is not possible. So when it comes to the problem solving techniques in various forms, so you can imagine analytical approach, experimental approach, numerical approach. So any kind of engineering problem, whether it is a structural problem or a computational fluid dynamics problem, or maybe heat transfer problem or a fluid flow problem, or maybe the combination of all these, can be solved by analytical approach, experimental approach, or numerical approach. So these are the different approaches. Analytical approach, you have to establish such kind of a equation, whether it is a differential equation or whatever the equation form. So the physical system need to be defined in a mathematical form. That mathematical equation need to be solved by taking the inputs and need to be given solution. So that kind of a system you can just think of. But if you see in a real life problem, all problems which are not involved in a basic level of problems, because if you just think of a complex problems will not be solved by the analytical expressions. So just think of a circle, x squared plus y squared is equal to r squared. So you cannot solve a bigger problem, aerofoil problem, by making that into boils down to simple equation, and it cannot be solved. And the only approach you can so think of experimental approach or numerical approach for complex problems. So you can do some kind of a prototype and do the experiments and then make a solution or get the results, and do the same thing using a numerical approach. So the complex problem you are dividing into n number of parts, and you are taking the solution for each part and integrating that solution to the entire problem. That is nothing but the numerical approach, where you will get a lot of solutions, and you can solve a lot more problems where you may not be able to solve using analytical approach. So these two are rapidly growing. You can think of numerical approaches, computational power. That kind of a computational power we have in the system. So if you look at the capacity of the processor, capacity of the systems, rapidly increasing, and the storage capacity or whatever the running capacity. So based on these kind of you can take the advantage of these kind of technologies to implement such kind of numerical approaches to solve any kind of complex problem. Experimental problem is a very old technique, and still it is a emerging technique where you can implement a very new approaches in the experimental approach. Also, most of the research areas you can imagine merging of any one or two or maybe individual and get the solution and compare and then provide the efficient solution or maybe accurate solutions. But if you just think of analytical approach, if you solve any problem, it will give a more accurate solution compared to the numerical approach. But where the complexity is involved, there you may not be useful. So this kind of analytical approaches may not be useful where you can apply the numerical approach to get the solutions. So this is a broader aspects, but what is the application and what kind of a solution you can get from all these approaches? And the first thing is which a type of approach is suitable to solve that particular problem. So that is the main important step to understand, and that need to be taken care to solve any kind of a engineering problem. It's not only thermal fluid sciences problem, but in a general sense, it may be applied for any kind of a problem, engineering problem. So if you just see the problem solving techniques, so I'll just have a look, the steps which need to be involved in problem solving techniques. First, start with the problem statements, schematics or assumptions or approximations, laws, properties, calculations, and you have to verify or validate or then discuss it whether it is suitable for your applications, and the expectations of the solving problem or the results are expected values you are reaching or not. That is also be important. That is itself establishing the efficiency of the problem solving technique. There are lots and lots of techniques. You can just look at this diagram where you can just get the solution straightforward. Maybe you can go round and round and round and then get the solution. That kind of a solutions may not be useful to get the efficient systems, where you have to see the validation as well as the efficiency of the problem solving approach. And there are some basic terminologies, dimensions, units, where the physical quantity can be characterized and the magnitudes assigned to the dimensions, which are calling as a units and dimensions. And these are the basic terminologies, open and closed systems. Maybe I'll just skip some of the content. Basic terminology, closed system, open system, where you just only one point I'll just explain this closed and open system. Energy and mass both are transferred from one to other, or maybe to the system to the surroundings. Energy plus mass, then it is called as a open system. If only is energy is transferring, that system we can call that as a closed system, where there is nothing is happening, that is termed as isolated system. Okay, thank you. So, so
Yes, Dr. Jawad?
yeah, I'm sharing
Yeah, we
this
can
screen.
continue. Yeah, yeah, yes, it's visible. We can continue.
Oh, Yeah. So if you just see the difference between extensive properties and intensive properties, where extensive properties doesn't depend on the mass and sorry, intensive properties depend on the mass, where extensive properties which will not be depending on the mass but depends on the size and extent of the system. And these are some of the continuation idealizations. These are we can have a look if you just have an interesting
On the chat WhatsApp, sir.
so this continuation idealization, I'll just state with a one word, saying that so these are kind of assumptions. Let's assume that just take a you know one rock or any object where you cannot expect each and every atom is connected with the other atom. So there will be voids will be definitely available. So if you are considering on a macro scale level, so that void should not be considered, and the whole system is a continuous. And if you are working on a macro scale level, then you have to have consider these voids also to understand the physical behavior of any system. So that is a kind of assumptions, or maybe some kind of a base of any to start with any kind of a problem. And this is also equilibrium state. So if you are not considering the state of equilibrium, any system is not in equilibrium, you cannot solve any kind of a problem. That is a basic uh, rule. Any system, any object, any problem, if you are considering thermal fluid sciences particularly, and you have to say that this system is in equilibrium. So if you are going for any kind of a dynamic problem, there it is changing rapidly with the time to time, every period of time. Then you might have the increasing the complexity of the problem. So that is a kind of a interesting area to learn a lot more rather than going for only the static problems where the equilibrium state is considered. There is has no unbalanced potential, so driving forces within the system. So that is a kind of a system you can just think of. What kind of equilibriums are there? Thermal, temperature, mechanical. There should be a pressure at any point in the system should be equal. Phase equilibrium. So what is that? What is that? So two phases, the mass of each phase reaches an equilibrium level. What is a chemical equilibrium? So chemical composition of the system does not change with the time. Why? So there will be, there is no involvement in the chemical reaction. Still more, you are adding so much composition in the system, but there is no change in the system. So that kind of equilibrium positions to solve any kind of a problem. So this is also one of the examples. And we may skip this process. So we'll come to the fluid mechanics. So just think about what is a fluid. So it starts with the fluid. So just a substance in the liquid or gas phase. And I think we have already discussed what is the statics dynamics of the system, where you can think of. So coming to the fluid mechanics is the study of interaction of the fluids with the solids, or other fluids with the solids, of course, other fluids at the boundaries. So any of these, if these kind of a problem, if you are facing in engineering streams, then you can just go to fluid mechanics and read out what are the basic principles and how to solve the problem. So this is the kind of a idea to implement. So one of the wonderful photographs they have pasted. So this is a wonderful simulation where you can think of a fluid flow. It is not only this particular automobile industry. There are lots and lots of industries are using this particular numerical way of approach to solve the problem, which may involve all these things, not only fluid mechanics. So it involves the heat transfer or energy transfer also might happen in the during the motion of this particular objects. So that is a kind of a study you can think of. So what is the difference between the solid mechanics and the fluid mechanics? I can just give one example with the one line. Solid can resist the applied shear stress by deforming. So it deforms continuously under the influence of shear stress. So that is the major difference. Shear stress is a lot to study in a fluid mechanics, no matter how small it is. Whether it is you are working on the micro level system or a macro level system, or maybe in a larger scale system, or maybe aerospace, or mm, uh, at the end spacecraft or something else. So you have to handle such kind of stresses which may affect a lot in the systems, and ultimately it gives uh, a bad results or a bad efficient systems. And so the research areas, if you talk about, so there are various research areas. So uh, thermodynamics is just a kind of a dynamic field of research and development. So that is applicable to almost all engineering applications, or maybe the energy generations or implementation of applications in our energy hungry world, because we are running short of the fossil fuels, or maybe non-renewable resources, what we call some fancy terms, you know. Um, so to develop any efficient energy system, you require to understand thermal fluid sciences. So whether it is just a paper industry, or fuel cell hydrogen research, or aerospace industry, developments in this particular thermal fluid science allows the world to grow more, or more sustainable use of energy to meet the requirements of the growing demands. Here we have, I think, I have presented some of the interesting areas. Development of energy efficient systems, where we talked about all these streams. Uh, Cooling techniques for electronic devices. I think you might have heard these terms, mining of virtual coins. So this is a fancy term in nowadays, mining of virtual coins. So let's say Bitcoin, Ethereum, or maybe etc. There are lots and lots of coins, virtual coins they're trying to develop. So if you see inside these big mining firms where they're trying to develop this mining, where they're developing these virtual coins, hundreds or maybe thousands of electronic devices are used. Which what is the result of this? A huge amount of heat generation is happening. So in these conditions, what is the requirement to solve such kind of a situation, to face or to handle or to deal with these kind of situations? One thing is efficient cooling techniques need to be incorporated, must be applied to run these systems in an efficient manner. So without that, you cannot expect to run these particular missions to generate or to develop virtual coins. And nowadays, this is a very, very emerging area, and you can just imagine in a stocks also very fluctuating area of the economic research. And if you see another research area, high efficient heat transfer. So that maybe we can talk about with particular applications. Just think of um, micro scale fluid flow and heat transfer. So next aspect is a refrigeration cycle and system optimization. So refrigeration cycle, it is a traditional concept only. It's not a new thing, but we can apply the new innovative ideas to optimize the cycle efficiency. So that is the interesting area to work with this thermal fluid science. So in fact, it's a never-ending process, because if you just imagine how this is possible with a conversion of 100% efficient system or a refrigeration cycle, never ever happen. But only hope is to improve the system. So people try to get that 100% cycle efficiency, but everyone know it never be possible. But they can try to maximize as much as they can. So that's where new models or new technologies are coming into the market, saying like a refrigerator with the improved efficiency, or maybe added new digital features, etc., etc. And these are the new uh, areas to work with. And you can think of a gas liquid two-phase dynamics. Another interesting area is the sub C architecture, so via reduced order modeling. So there's a word called reduced order modeling. So well, reduced order modeling in a sense that assume if you want to analyze any 3D model, which is actually a very complex system, and it is very difficult to understand the physical behavior of this particular system. Such kind of situations or maybe such kind of a problems where you can apply these reduced order models by uh, reproducing from 3D model to 2D or maybe 3D model to 1D itself. So this kind of approaches reduce the complexity, and we have to be very careful if you are doing this process to provide the approximate solution. So it is very important. So that is the where we should not compromise the accuracy of the solutions. That is more important if you are understanding the reduced model approach. So how this is happening? You just imagine one big structure of aerofoil is considered as a 1D body, and then you are analyzing that 1D body using some of the models which are already existing, and then get the solution which is exactly matching, not may not be exactly matching, which is at least reaching to the approximate solution, to the analytical solution, or maybe the experimental value. Then you can incorporate these kind of approaches, or maybe the models to work with. So there are very interesting softwares also are available, not only for computational fluid dynamics and kind of a study for multi-physics or maybe other approaches. So there are considerable number of softwares which are available. So there in the background, you can think of these kind of a models can be implemented. Just imagine software is not built with something which is not beyond our limitations, which is just a background where you can incorporate some of the models where analytical approaches or maybe some kind of numerical approaches. You just give the input in the programming language, then so any problem can be solved using just one click or maybe with a set of inputs. So that is the advantage of using interesting or emerging softwares. So interesting area where you can research in developing efficient fuel technology. In this area, challenging task is analyzing COPV. This is a new term, I think, for many of the audience. COPV is a composite overwrapped pressure vessel which is surrounded by extreme thermal effects. So this is automobile application. You can imagine there is a one company called Faurecia. They are very much interested to develop or to implement some kind of research in this particular area. COPV, composite overwrapped pressure vessels, which is surrounded extreme thermal effects and analyzing the fluid flow behavior of hydrogen inside the COPV tank. So that is a composite over wrapped pressure vessel tank. An understanding of these physical systems is a very, very interesting area of research where you can see the thermal effects, where it can influence the or it can explain the behavior of COPV, composite overwrapped pressure vessels, or maybe how this fluid is behaving within the tank of which is filled with a hydrogen fuel. And you might have heard about this news recently. NASA achieved another milestone in a human history that one of its spacecraft called Sparkus Solar Probe managed to make a contact with the sun's upper atmosphere. It is not only managed to survive in such extreme heat conditions and also manage the energy conversion. So this is not a simple problem to solve. There are thousands and thousands of scientists and engineers and a lot more people are involved to solve these problems. It is not one person can solve these kind of complex problems. So it is a hand they can, or maybe they can provide some sort of solutions in a part basis, but you cannot solve on your own, but you can work together with a team to solve such kind of problems. So as a result, for this particular Sparkus Solar Probe, which provides many unknown secrets of the sun's atmosphere, which may be new for many of the audience, but it is true that is all about heart of our solar system. So in a general sense, this thermal fluid science is a really challenging field which offers exciting opportunities in the development of more efficient fuel and fuel systems and maybe new energy sources, biomedical equipment, or maybe other areas where you can work with, especially in a recently rapid emerging areas such as EV technology in the automobile sector, space technology, where applying these fundamentals of thermal fluid science is very important. Understand their physical behavior and interesting also, which ultimately helps to develop efficient system. So, as a final note, thermal fluid science has a long future and provides great opportunities to the expertise engineers in this particular field. So, with this, I'll end my webinar. So, you can ask me any queries if you have. I'm happy to answer you and interact with you in this regard. Thank you. Over to you.
Thank you, Dr. Jagat. Thank you for the informative session. So, leaving apart our technical disturbances, that was really a interesting session. Thank you, participants, for your patience listening. So now we are good to take questions. So you can drop them in the chat box, and I'll put the questions. I'll list out the questions to the instructor. Participants, you can drop your questions in the chat box. Questions from the participants? Yeah, we have the first question, Dr. Jagat.
Yeah, can you read it?
It's from Balaji. How can we able to design mathematics model for custom design of thermal system?
What is that? Custom design of?
Yeah. How can we be able to design mathematics model for custom design of thermal systems?
Yeah. So the name suggests the custom design of a thermal system. So where you can apply some of the numerical approaches such as volume method or maybe emerging XFEM method or such kind of numerical approaches you can just think of to implement, where actually the mathematical equation, direct equation, you cannot get it for any kind of a application or maybe any kind of a problem. But in a overall, we can think of approximate solutions only, because you are talking about the custom oriented thermal systems where so you categorized in such a way that it need to be given inputs and get the outputs in a particular fashion. So that is a customized kind of thing. But so you may not get the analytical approach solutions, but you can just work on the numerical based approaches. Best methods are available where you can take some of the programming languages. Just a bit is required. It's not much. You can code it and then import that particular geometry into the system and then apply these particular some of the numerical approaches. So with this, you can just give an input, let's say, so this much velocity of the fluid, or maybe how much thermal effects are influencing the system, or maybe what is the energy is transferred, or how much energy is utilized, and what is the internal energy of the system. So by giving all these inputs, you can get the expected results by using some of the numerical approaches. But I think you may not be able to get some kind of a analytical approaches to solve these kind of problems. Yeah.
Thank you. The next question is from Rajat. How to control heat radiating from battery of EV cars when they are at their top speed in warm environment?
So this is comes under dynamic conditions absolutely. If you just think of how much rate of the fluid is transferred from input to the output, and then you imagine how much heat is transferred and how much fluid is transferred. So if you have a control or maybe sensing devices where the input and output maybe in between or inter layup also. So if you have a control over the fluid flow into the system, then obviously you will get a better results or maybe efficient approach, efficient system you may expect. If you have a control over the fluid flow or maybe the heat transfer rate at which the heat is transferred from one state to the other state or maybe one system to the other system. So that kind of a control. So nowadays you can think of IoT based technologies where you just get the information. You may not be there, not only in the radiator, it may be, it may not be in automobile sector somewhere, other industrial oriented systems also. So there you will get the control over the whole system, not only the radiator, all thermal relevant or thermal fluid relevant systems. So with that control over the particular system, you can expect the efficient results. Rather, in a old traditional approach, you may expect kind of good results. So I think the controlling of the system, how to control the particular system, whether it is the radiator or any other system, how to implement such kind of technologies where you get a maximum control over the system. So that kind of a solution you can provide to understand the uh, actual system and get and expect such kind of efficiency in the system.
Yeah. The next question is, at what level CFD will be considered in the course?
Well, CFD is emerging technology. Obviously, we don't have a choice to skip or maybe to just give introduction in the course, but definitely this will have a huge role in the course because CFD is directly related to the particular thermal fluid sciences, where you can just see the flow of a fluid or exchange of energy or whatever the way you just think of in a aerofoil system or not only refrigerator, not only in other applications, all applications, direct solutions, there are no solutions in an analytical approach. So you have to work with numerical approaches only. So I think CFD is emerging area of understanding any kind of a physical behavior of thermal fluid sciences, and it definitely have a huge role in the particular courses, not only this course and even in any basic level of understanding of thermal fluid sciences. The CFD is the understanding of basic principles of CFD is also required, and in this course also we include it. Yeah.
The next question is from Krishna. How to predict fluid structure interaction like aircraft or re-entry vehicle?
Yes, yeah, this is an interesting area. One of my colleague is also working from the past 6 years, FSI problems, fluid structure interaction, where actually this requires not only the heat transfer, thermal fluid sciences, and the three streams of knowledge is not enough to understand FSI problems. Why? Because there is a structure is also involved in this particular concept. So if you are working on the composite level, just imagine a wing of an aeroplane, lots and lots of stiffened panels, composites, or other kinds of materials which are involved. So these are structural based concepts need to be understand. then only you can work with the FSI problem, merging with all these three streams. Without knowing the structural point of view, there's no question of understanding the FSI problem, because the understanding of how the structure behaves without knowing the behavior of the structure, there's no question of understanding of the how these affects, whether it is an aerofoil structure or wing or internal frame of a aeroplane, or maybe not only this automobile sector also now they are trying to use the composite based structure. So there also wide body frames, there you might have seen composite materials they are trying to use in the design and development of the structure. So structural interaction is very important, and the structural interactions with thermal and fluid and transfer effect. So merging of this will give the solution of FSI problem. And this is also a kind of a numerical approach only, because uh, many of the researchers are working on this particular area, and they are giving their best solutions for a different kind of applications. And so this is a also good area to work with.
Thank you, Dr. Jagat. So that will be the
Yeah,
end of our question and answer session.
thank you. Yeah.
Thank you, Dr. Jagat.
Yeah, thank you for giving me this great opportunity, and I'm looking forward to see more some more great opportunities. Thank you so much. Have a great day.
Thank you, Dr. Jagat.
Bye.
Bye. So participants, you can start filling the poll. So once the poll is done, I send the link for the certificate in your chat box. So your certificate will be generated in 5 to 6 days. Once all the participants complete the polling, I'll send the certificate link in your chat box. All the participants kindly fill in the poll. Once the poll is complete, I'll send you the link for the certificate. All the participants kindly fill the poll.